Hello, good afternoon. We are the Manhattan College team, and we will be discussing the energy recovery from fats, oil, and grease, otherwise known as fog. In our presentation, we will be introducing energy recovery from fog characteristics, energy recovery processes that we evaluated, such as codigestion and biodiesel, process selection, our preliminary process design, as well as preliminary cost and revenue estimate. Fats, oils, and grease are byproducts of food preparation, cooking, and cleaning, and they're basically compounds that consist of fatty acids and glycerol. Although fog is typically made up of fats, oils, and grease, it can also include inert material from the wastewater. It enters the wastewater collection systems from both domestic and commercial establishments like restaurants and food processing businesses. Some examples of fog are vegetable oils such as palmitic oil, linoleic oil, and oleic oil, as well as animal fats. As stated before, there are many problems associated with fog, especially in our collection systems as well as our water resource recovery facilities. Deposits can coat walls of the sewers, reducing capacity and causing blockages within pipes, resulting in sanitary sewer overflows. When it enters the water resource recovery facilities, it accumulates in wet wells as well as the surface of primary sedimentation basins. This can result in odors, housekeeping problems, and disposal costs.
So what is the value of fog? Although fog is a waste product, it has many potential beneficial uses. Fog has the potential to create energy and can create biodiesel. Using fog as a feedstock for biodiesel production significantly reduces the cost of the biodiesel production process. The use of this produced biodiesel can then reduce greenhouse gas emissions and many criteria pollutants. If used for anaerobic codigestion, fog can be used to enhance biogas production. And the reuse of fog results in less waste that needs to be incinerated or placed in a landfill. The overall goal of this project is to determine and evaluate the best method for capturing the energy in fog. The important characteristics of fog were determined by a study done at Manhattan College. The study involved taking samples from 3 New York City water resource recovery facilities over a period of 6 months, with 12 samples taken from 2 locations at each facility. The purpose of this study was to understand the different characteristics of fog, understand how these characteristics varied among the various water resource recovery facilities observed, and to evaluate the possible uses and disposal options available. From this study, several important characterization parameters were determined to assess how and if the fog could be used. These parameters included chemical oxygen demand, N-hexane extractable material, energy content, volatile fatty acids, total and volatile solids, metal content, and density. The results for the majority of these parameters were consistent among the facilities. However, variations in total solids and energy value were found among 3 facilities.
Now we are going to introduce each of the 2 options we consider for beneficial reuse and energy recovery of fog: codigestion and biodiesel. Codigestion is a process that mixes high-strength organic material with wastewater sludge. This mixture is then fed to an existing anaerobic digester at a water resource recovery facility, where the sludge is stabilized and a biogas containing methane is produced. Food waste is most commonly used as this mixed feed. Codigestion at specific levels is shown to enhance both biogas production from the digesters as well as the methane concentration of the biogas, increasing the total methane yield from the digestion process. As the process will incorporate a greater feed supply and increase biogas production, excess capacity in the digester is crucial for the feasibility of codigestion. There are numerous advantages of using fog for codigestion. Currently, one New York City WEF codigests food waste with its sludge. The consistent results from this facility confirm that codigestion can enhance methane and biogas production. Literature review indicates that fog codigestion specifically will also enhance biogas and methane production. Another factor we considered is the fact that some New York City digesters currently have excess capacity necessary for codigestion, making the process feasible. However, there are some notable disadvantages to the process. Due to its characteristics, fog is more difficult to handle and convey than food waste is. Also, fog is only beneficial to the digestion process up to a certain point. At loading rates higher than around 50%, fog inhibits the production of methane. Because of this, the entire supply of fog is likely not able to be used in codigestion. This creates additional problems and costs for storage and disposal of unused material.
Biodiesel is a renewable and biodegradable fuel composed of a mixture of long-chain fatty acid esters created from refined plant and animal fats. Biodiesel production is a viable alternative to the co-digestion of fog, as proven by existing literature in plants. The same waste products used to supplement anaerobic digestion are instead processed through transesterification and purified through vacuum distillation to create high-purity biodiesel. Biodiesel is a green alternative to petroleum distillate diesel, as the US EPA has shown that there is nearly 75% reduction in low life cycle CO2 emissions. Traditional biodiesel production in using soybean oil, for example, has a total of 75% cost in just the feedstock. In using fog from wastewater recovery facilities and grease trap waste, we can reduce our total cost by that amount. Biodiesel offers a more efficient energy capture and recovery process than co-digestion, which is sensitive to temperature and toxic contaminants present within the fog. The biodiesel process we have chosen is chemically induced and is not subject to the upsets of a biological process. Even with a low-quality feedstock, the process will carry out in the same amount of time and produce a high-purity product. All of the fog input into our plant will be processed, unlike co-digestion, which requires excess capacity to be maintained in case of large loads. Biodiesel can be sold for $3.52 per gallon, producing a high revenue. A plant with a distillation capacity of 10 liters cubed per hour was shown to have a revenue of $1.8 million USD per year. Compared to co-digestion, biodiesel does have upfront disadvantages. Biodiesel needs a completely new facility, and as such, operators are also unfamiliar with these processes. There is high sulfur present within our feedstock, which needs to be removed through vacuum distillation.
To determine which process is the best, we use a decision matrix based on scoring and weighting factors. We use several categories consisting of process considerations, costs, process control requirements, energy benefits, as well as aesthetics. As one can see, our scoring key was rated from 1 to 5, 1 being that this parameter has a negative impact on the overall process, whereas 5 means that the parameter has a positive impact for the overall process. Our weighing key was on the same 1 to 5 scale, whereas this time we looked at whether or not the parameter was significant or not to the process. Here we looked at process considerations and costs. And as you can see, process considerations had a high weighting factor and had differing scores for co-digestion and biodiesel. For example, the capacity for feedstock utilization was much higher for biodiesel at a score of 5 than compared to co-digestion, which scored 2, because in co-digestion we would only be able to utilize a certain percentage of the incoming fog, whereas biodiesel we utilized the entire fog coming in. Here we looked at process control requirements, energy benefits, and aesthetics. As we can see, again, biodiesel is leading ahead in terms of scoring for all of our process considerations and parameters. So therefore, we selected biodiesel as our final process. Some of the process consideration that we looked at for biodiesel included the fog receiving station, what's needed for pretreatment, as well as the biodiesel production process, which includes esterification, transesterification, and purification, and lastly, storage. Our block flow diagram breaks down our biodiesel production process. So we have an incoming fog, which is pre-treated using filters as well as acid degumming, followed by esterification, which essentially converts our fog into fatty acid methyl esters. Then we have transesterification, which essentially uses a catalyst to form fatty acid alkyl esters. Our final step is the post-treatment process, which includes vacuum distillation as well as another filtration system for refining. This will generate B100 biodiesel fuel up to ASTM D6751 standards.
This is the process flow diagram for our system. Pretreatment ends on stream 14, transesterification ends on stream 21, and our biodiesel is recovered in stream 27. The other streams from purification, such as W7, W8, and W6, are lighter and heavier fractions of our biodiesel, volatile organic compounds, and esters and glycerides.
The first step in the treatment process is the fog receiving station. Fog will be collected from inside the WEF as well as from trucks bringing in outside fog, such as from restaurant grease trap waste and other participating treatment plants. Fog from inside the WEF can be collected off the surface of various unit processes into containers, and the containers can be directly discharged into the collecting well of the receiving station. As previously mentioned, external fog can come from grease traps from places like restaurants and food processing facilities. On average, trap grease is composed of 95% water, 3% solids, and 2% brown grease. Brown grease contains a large amount of free fatty acids, which need to be removed in pretreatment. Other participating WEFs can also collect fog from the surfaces of their processes and haul it to the receiving station. At the receiving station, trucks back into the unloading area and discharge into the collecting well. In the collecting well, excess water can be drained and returned to the plant headworks. The collected fog will then be pumped to the pretreatment stage.
After the fog enters the fog receiving station, it enters the pretreatment section of the process. The pretreatment of the fog consists of 3 different processes, including inert removal, acid degumming, and neutralization. Different studies, such as the one done by Manhattan College, showed that fog has a very high quantity of these inert materials, specifically different plastics and fibers. Now, these have to be removed before the biodiesel process due to their effect on the efficiency of the process. They cannot be converted to the biodiesel, and they could clog and just overall affect the different equipment used throughout the processes. Now, possible technologies that could be added to the design of the plant in order to remove these inerts include chopper pumps and drum screens. The chopper pumps grind the inerts down and make them become almost a part of the fog. That way they can be treated along with the fog. Drum screens, on the other hand, completely separate out the inerts, which makes them easier to be removed. After removing the different kinds of inert materials from the fog, it enters the acid degumming stage of the pretreatment process. Now, acid degumming consists of adding water to the feedstock, then agitating it using some sort of mechanics, and then combining the feedstock and heating it before using separation processes such as filtration or settling in order to remove the phospholipids and gums from the fog. Acid is then added. Now, typically it's phosphoric or citric acid in order to further hydrate those particles and remove them. The phospholipids and gums are important to remove from the fog because further down throughout the rest of the processes used to convert the fog into biodiesel, they could react and form different insoluble particles. While that is something negative that could come out of the acid degumming, one of the benefits is that it does convert some of the free fatty acids into FAME, or fatty acid methyl esters, that are important for the biodiesel process. They can also enhance the glycerol separation that occurs later on down throughout the processes. The last stage of the pretreatment process is neutralization. Neutralization is when an alkali solution is added to the feedstock. This solution helps neutralize any of the acid that was added during the acid degumming stage of the pretreatment. It also removes some of the free fatty acids from the feedstock by producing soaps. These soaps are insoluble but can later be removed through water washing. The neutralization process also removes some of the unwanted particles that could affect the color and quality of the feedstock itself. Some of these unwanted particles include trace metals, sulfur compounds, and soaps.
Transesterification is currently the most common reaction used to produce biodiesel. The reaction takes place between triglycerides, in this case fog, and an alcohol, usually methanol, to produce biodiesel in the form of fatty acid alkyl esters and glycerin as a byproduct. The overall purpose of this reaction is to reduce the viscosity of the oil so it becomes less resistant to flow and more prone to combustion. Due to the poor surface contact between the reactants, a catalyst is generally needed to increase the rate of the reaction. An acid or a base can be used for this process. Here's an overview of the chemical reaction mechanism taking place using a base as a catalyst. The base reacts with alcohol to produce a negative alkoxide and a protonated catalyst. The triglyceride then undergoes a nucleophilic attack by the alkoxide to produce a partially negative tetrahedral intermediate. This molecule is then split in half to form an alkyl ester, which is the final biodiesel product, and a diglyceride anion, which will eventually produce the glycerol. There are a wide variety of catalysts that can be used for this reaction. These catalysts can be either heterogeneous or homogeneous, and basic or acidic. In this case, we chose magnesium oxide, which is a heterogeneous base catalyst. A heterogeneous catalyst has the advantages of easy separation after the reaction is complete, as well as being able to tolerate more extreme conditions, has a high yield of biodiesel, creates a highly pure glycerin byproduct, as well as being inexpensive and having a large specific surface area. A basic catalyst has the advantages of modest operation conditions as well as being widely available and inexpensive.
Once we have produced the crude oil from transesterification, the biodiesel needs to be purified. We have chosen vacuum distillation for this as it removes odor-causing compounds, sulfides, is economically feasible, recovers unconverted material, meets ASTM 6751 standards, and it also removes colored impurities as well. The main parts of our process are esterification, transesterification, and vacuum distillation. The yields and conversions for these are as follows. Esterification and transesterification each have a conversion of 99%, and vacuum distillation has an overall yield of 85%. The overall yield for our process is 83.3%. However, this does not include recycling material recovered in the vacuum distillation. Including this would increase the overall yields of our production process.
Throughout the biodiesel production system, many of the unit processes require a consistent feed. Fog will therefore be stored at various locations in the system in equalization tanks prior to these unit processes. Progressive cavity pumps are recommended for the initial conveyance of fog through pretreatment. These pumps are specifically designed to handle thick and viscous material and can handle solids concentrations of up to 7%. Progressive cavity pumps also use positive displacement, meaning the pump will produce the same flow at a given speed no matter the discharge pressure, which makes it easy to regulate the pump flow by simply regulating the pump speed. After the decanting stage in esterification, it is assumed that any remaining solids will be negligible to pump selection. Therefore, all remaining pumps will be centrifugal pumps, which are economical and widely used for lower viscosity fluids such as biodiesel.
Project cost estimate. As previously stated, the feedstock is typically the greatest cost in the production of biodiesel. Because we are using fog, which is a waste product, there is no cost of feedstock and the process becomes much more cost-effective. Approximate costs were estimated by looking at capital costs of existing biodiesel production facilities with similar capacities. According to our calculations, the total equipment costs were estimated to be about $195,000. This does not include construction costs. Quality control costs for the testing of laboratory equipment and to ensure standards are met were estimated at $70,000. Operation and maintenance costs would also need to be taken into account, however, they were not calculated in this case due to only having a preliminary design. There are several ways in which biodiesel production may generate revenue. Because fog is an unwanted waste product, companies may pay tipping fees of up to 8 cents per gallon in order to get rid of their fog. Government incentives may be available, such as a $1 per gallon biodiesel mixture credit, which creates an incentive to mix biodiesel with traditional diesel fuel. The selling price of biodiesel itself varies with market values, but typically can be sold for around $3.52 per gallon. The pure glycerin that is produced as a byproduct can also be sold for approximately 3 cents per gallon. And finally, it is expected that this project will qualify for low-interest financing through the Clean Water State Revolving Fund by placing the project on the annual intended use plan.
Lastly, we would like to give a special thanks to Professor Jeanette Brown and Logan Graney of Manhattan College, as well as Richard Pope from Hazen and Sawyer. Thank you so much for your assistance in this project.